Hello, and welcome to episode number 18 of CS350 Online. I'm your host, as always, Leslie Ested, and in today's episode, we are going to continue our discussion of I/O and devices. In particular, we are going to be focusing on disk drives and the drivers for those disk drives. So if you're following along in the textbook, and again, that's completely up to you, the section that you might be interested in is I/O and devices. And again, I just want to do a quick reminder not to forget about the quizzes and reading assignments that have been posted on Learn. The reading assignments are only available for about a 7 to 10 day period of time, so make sure you get that in there before the deadline. The other thing I wanted to say about them is that it's really important you read through the paper a couple times before you try to write the quiz. Don't try to write the quiz while you're reading the paper. You might be able to make it work, but I don't want to make any promises about that. So do read the paper first. All right, so to start off today, and yes, I checked my mic this time to make sure it was working. Let's go to the OS of the day. Today's OS of the day is called Minix, and you might have actually heard of this. It's an operating system which I think is actually still out there. I've never actually used it myself. But this was created in 1987 by someone named Andrew S. Tenenbaum, who has also written a number of operating systems textbooks. And he was trying to create something that was like a miniature version of Unix. So Unix is everything in the kitchen sink goes into the kernel. So it's a monolithic kernel. And that means that it's very, very big and includes all these crazy drivers, all these crazy features, there's a lot in it, and there's a lot to read if you try to sift through the kernel code to learn anything about it. So he wanted to create a microkernel version of a Unix-like operating system. And so that's what he set out to do with Minix. And it was originally written in C, as most operating systems, let's be honest, actually are. Many of them are written in C, and there's good reasons for that. C is a lovely low-level language. It works really, really well for interacting with assembly, and it's pretty quick, and so on and so forth. The original kernel was only 12,000 lines of code, and that included the kernel, the file system, and memory management. So that was a lot of stuff for 12,000 lines of code. Now, I actually have the code to, I think, Unix version 6 lying around somewhere, and it's even smaller, and it's like an inclusive one, but it's also a lot older than Minix, so it doesn't have as much functionality as something like Minix would. So one of the interesting features of Minix was it was designed to be this concept of self-healing. Now, that's a really bizarre idea, except it's something that actually shows up in most operating systems now. So the idea is that it's pretty common for device drivers to crash. And I'm sure any of you that have had a real graphics card in your computer have noticed that the graphics card driver likes to crash, especially like NVIDIA ones and ATI, or I guess they're AMD now. They crash a lot. And when they crash, they take down your whole system. You get the lovely blue screen of death. So what the idea behind Minix's self-healing was instead of having the device driver crashing because of kernel panic and a blue screen of death or what have you, they wanted you to be able to restart the driver without actually affecting the running process. So this is actually a really interesting idea. So the concept is the process wouldn't terminate. It would be paused. So it would go from like running back to some kind of I want to say a blocked state, because it would be waiting for the driver to be restarted. And then what would end up happening is instead of the kernel panicking, the kernel is actually going to take the driver down and then like stop it if it hasn't stopped on its own, and then it's going to restart it. And that's actually, if you're looking at a Linux or Unix-based operating system, that's actually not too bad. You can use modprobe to unload and reload kernel modules. And for example, if you're like turning on some networking features, this is actually a pretty common thing to do, because you'll change a setting in some kind of networking system, and then you'll have to restart the driver, and that's totally normal. And you don't even have to restart your computer. Maybe, of course, they got this idea from Minix, but so this is actually a really nice feature. And then the idea is, since the process that was running during the crash isn't actually terminated. It can actually continue about its business afterwards, after this pause to restart the driver. So this actually makes it quite reliable. Now, it said that this operating system is actually the inspiration for the Linux operating system, which you'll notice we still haven't talked about. They said that Linus Torvalds, who's the one who wrote the Linux kernel, he actually used Minix to create Linux. So while he was implementing Linux, he was using the Minix operating system. Rumor has it that some people were trying to have a lawsuit saying that Linus copied the code from Minix, but apparently the architecture and the code is very different, and it's very obvious that was not actually the case. Oh, excuse me. All right. So that's our OS of the day. Yes, we will get to Linux at some point, but not today. So let's look back at where we were. So we have been talking about devices and device drivers. And again, just to reiterate, because this was like 5 days ago and I know so many things happen over the weekends, devices are things that we usually think of as being attached to our computer externally: a monitor, a mouse, a keyboard, a printer. They're input and output devices, but there's also a lot of devices that are part of your computer. It's not like something you can physically take is a device. It is inside your computer. It's not like something you can physically take out. Wouldn't want to do that. But those devices are still very, very important. It's also things like your disk drives, which offer you persistent storage, things like serial consoles, which is taking and printing characters up to a console, looking at things like your network interfaces, which might be on board or might be a separate card. I know on this computer I'm using right now, the network card is on board, but my other desktop computer, which is downstairs, its network card is not on board. I mean, it does have an onboard one, but I have a 10 gig card in it, and yeah, so it's a separate physical card, but it doesn't have to be. All of these devices are input or output devices. Some of them are both, and the operating system needs to be able to interact with them. And we talked about how every device has this little spec sheet that lists a bunch of device drivers, and the device registers. And device registers are actually registers that are on board the physical device. And that is, each of those different device registers can be used to either learn something about what the device is doing or tell the device to do something. So we have status registers to tell us something about the device. And then we have command registers for us to tell the device to do something. And then we have data registers, which we use for larger data transfers. Now, sometimes these registers get combined together, so that status register would typically be something you read, and a command register is something you would typically write to. So you can make a status and command register where reading does one action and writing does another. And this is actually a pretty common thing because registers actually take physical space. And so we don't want to have like an infinite number of registers to do all the different tasks. We want to minimize the number of registers because, again, we want to minimize how much space we're taking on the onboard. We looked at a couple brief ideas of how to create a device driver. So one of them was using this concept of polling, keeping in mind that we usually need serial access, so mutual exclusion on a device when we're interacting with it. So we use semaphores for that. And we could poll the device and keep asking it, are you done? Are you done? Are you done? And then when it finally says, yes, I'm done, we can release the semaphore, so release our lock on the device. That's one way, and that's polling, and that's actually what USB devices do. Or we could do a two-part model, which is also very common, and that is where you have something that actually initiates the task with the device of the driver handler, which is going to take out the lock on the device, so create the mutual exclusion, and then it's going to tell the device to do something. And then we have a separate interrupt handler where when the device throws that electrical signal to say, hey, I'm all done, we can finish up with the device and release the mutual exclusion on it. And the advantage to this is there's no polling, you're not wasting CPU time, and the other advantage, of course, is that since you know that it's pretty unlikely that the thread that initiates contact with the device will very unlikely be the same thread that actually receives the interrupt, using a semaphore for mutual exclusion here makes a lot of sense. So this is another way to do it. It's not that you have to use a semaphore, you certainly could use a lock, but this is a bit more efficient. All right. We also talked about how you actually get into these device registers because it's not so easy. You don't just know, oh, here's all the registers and I can just start using all these instructions, because the assembly language of your computer doesn't know all of the different devices that you could actually plug into it, because there's new devices being released every single day. So how could your architecture know about all of them? So we do these mappings. So there's port mapped I/O, where we actually have a separate address space that uses fewer bits to address it, such that instead of calling it addressing, we actually call it port numbers. And then we use special I/O instructions to actually move data to and from this special piece of memory. And we bind these port numbers to device registers on boot. So that's kind of neat. Now, the advantage of this is that since this bus that connects the CPU to the this port mapped memory region is really only used for devices, it's actually a bit more efficient, because the devices are going to have to, when they're attached to this bus, they're going to see all of these instructions and they have to decode the addresses to ask, is this address one of those ports that I'm mapped to? But since all of the addresses that are flying by are all related to this port mapped memory, it's very likely that you're going to come across an address that's for you. But not only that, there's going to be fewer address translations that you need to do. The downside, of course, is that you have to use the special I/O instructions, which are very restrictive. And there's not very many ports because we don't use very many bits for this. So it's kind of restrictive, but it is better performance. The less restrictive model is memory mapped I/O, where instead of using special memory, we just use RAM. So we just use regular load word and store word instructions. And again, we're just going to bind regions of that physical memory to device registers. But now the devices are connected to the main bus. And the devices are going to have to translate every single address they see come over the main bus to ask whether it's for them or not. And the number of addresses flying down that main bus is significantly more than the other bus. And so it's a little bit slower because the device is going to have to translate this to say, is it for me? Is it for Amy? Is it for me? Except it's just you loading elements of an array half the time. So it's a little bit slower, but it's a lot more flexible. And it's not that a computer has one or the other. Your computer actually uses both of these technologies. And in OS 161, we do use memory mapped I/O. And in fact, the region of KSEG1 that we use, which maps to the very last chunk of the 512 megabytes of physical memory, is actually where we are mapping our devices to. So we have 32 slots of 64 kilobytes, and each device get mapped to one of those. So that's kind of cool. And then for larger transfers, so let's say you needed to transfer like megabytes of data, you have options where the CPU is actively involved with the transfer. And then we have, and that's program controlled I/O. Of course, that's a little slow. And then we have direct memory access, which is what computers use today. And the idea behind that is the device is responsible for actually performing the memory transaction going to and from the actual device. So the CPU is free to do something else. And this is a really high level look at it because there is actually a physical device called a DMA controller that's involved here, and we haven't even mentioned that. But again, we're just looking at a really high level. And your computer does both of these. It's not that it can only do one. Your computer will do both. OS 161, on the other hand, just does programmed controlled I/O because it doesn't have a DMA controller. All right, now I want to move on to our new topic. And sorry, I didn't realize I had the corner of my desk in there. The new topic today is looking at persistent storage. So this is any kind of storage where when there's no power, the data remains. And what's really interesting about this is that the concept of persistent storage has been around for a very, very long time. And I mean, if you think about it really, even something like a book is a form of persistent storage. Somebody carving into a rock is persistent storage because it's going to stay without power and it stays for a really long time. But if we were to just think about persistent storage in terms of programs and data storage, like in a more programmatic method, then the concept of persistent storage actually dates back to the 1700s and the Jacquard loom. Now, you might have heard of that, the Jacquard weaving loom. But, I had a picture of one here the other day. I was watching. Somebody actually still has a Jacquard weaving loom that works, and it's really, really cool. I was watching. Oh, it was a video on YouTube I saw. Anyways, maybe I'll post a link on Piazza for you. But once upon a time when people were weaving fabric, it was a bunch of people doing it by hand. And if they were trying to create this pattern that they wanted to replicate over and over to create, a certain pattern in fabric, it was up to the human to make sure that they have the right threads up and down so that they could produce the correct pattern each time they pushed the little shuttle through the fabric. I don't know if you know anything about weaving. It's a very painstaking process. The problem is humans make a lot of mistakes, and I'm sure you know that because you write code and you make a lot of mistakes. With me, I add the letter E to the end of words where E is already there at the end or doesn't belong. That's just a weird thing I do. Everybody has little quirks. You make a lot of mistakes. So somebody had the idea of, what if we could create a loom where we could eliminate the need for human to figure out what the next row of the pattern is. And this is kind of where the Jacquard weaving loom came from. They were able to create this loom where the pattern was, or the instructions to produce the pattern was stored on a sequence, of punched metal cards. And the metal cards were like stitched together with twine or wire. And as you moved through the weaving process, the pattern would rotate to the next. So it would be like, okay, here's this row of the pattern. And so the loom, based on where the holes in the card were, would adjust the threads automatically for you. So you didn't even have to think about that as a human. And then you put your shuttle through, and then you pull a crank, and it moves to the next row, and it moves to the next row on the metal card. So it was a programmed loom, and the pattern, the program, was on these punched metal cards. And what's interesting is, so that's been around since the 1700s, and we actually used this concept of punched paper or punched cards through the 1970s. So that's actually one of the most persistent forms of storage we've actually ever used. Now, what's interesting is that, so we, in the early 40s and 50s, we used punched paper cards. They're about that big. I used to have a stack of them. I don't anymore. At one point, I think we were wallpapering part of the CS club with them. It's a cool decoration, right? We were using punched cards and 30-pin Sims around to decorate the office. It's cool. Anyways, after using punched cards, now obviously the problem with punched cards is that they were paper, but at least they were cardstock, so it wasn't so bad. But then we actually moved on to punched paper tapes. We used punched paper tapes through the 70s, and the problem, of course, with a paper tape is that it's very thin and it's very fragile. And so it was really common for when people were making copies of these paper tapes, for the paper tapes to actually get destroyed. So they were not very durable. Now, something else that came into play was this concept of magnetic drum storage, or magnetic tapes. Now, the magnetic drums were these big drums of like a ferromagnetic material, and I'm just trying to adjust my light here. The ferromagnetic material, based on the orientation of the magnetic field, would either be a 0 or a 1. That's kind of cool, right? And this has been around since the 30s. And we've used various forms of magnetic media over the years. So it was drums to start with, and like these big magnetic drums. And then another thing that we've also used was magnetic tapes. And magnetic tapes has actually still in use today. And what's really interesting about magnetic tapes is that they're actually still in use today. And in fact, if you go on to any computer website and you type for magnetic tape storage, you can actually buy it still because people still use it. So I'm just like, I'm trying to buy one right now. So if I try to buy magnetic tape storage, it takes me to Amazon Business. I don't want that. Why isn't that showing me? It used to be so easy to buy these. Newegg. Maybe Newegg will tell me. So like you can buy a tape drive from Newegg for less than $150. And then the actual magnetic tapes themselves, I can buy, it looks like a pack of five magnetic tapes, that each, in the capacity of each magnetic tape is 1.5 terabytes. And for a pack of 5, it's $240. That's actually one of the more expensive ones I've seen. Maybe that's because it's a funny brand. But the point I'm trying to make is that we actually still use magnetic tape storage today. What magnetic tape is maybe you've seen this, a cassette tape, an 8-track, or a VHS. It's a thin piece of plastic that's coated in this ferromagnetic medium. And again, we're altering the magnetic field to be zeros or ones. So reading them is a linear process. You can't do random reads and writes. You actually have to move the tape physically to the correct position and then rewind it back to whatever position you want it to go back to. So you fast forward and rewind. So now you might be asking, why are we I said you could still buy it today and it was cheap. Why can you still buy this today? Why do we still use magnetic tape storage today? Actually, the reason is it's really good for archiving. So if you, for example, University of Waterloo, we absolutely use magnetic tape storage for archives. Absolutely, completely, totally still use it. And the reason is it's cheap. It's really, really cheap to use it. And it's really good for longer term storage. Because the cost per byte is cheaper than using a mechanical drive. And you actually see it used in the film industry a lot. So film industry, they actually keep an archive of all the different footage that they ever captured for every film. They actually keep it because, how do you think they released 15 years later this special edition with 8 extra minutes of footage? Well, the reason why they were able to do that is because they actually archive every last clip, every last shot that they ever took. Every take is archived, and they do this archive on magnetic tape. And it's good if you don't have the expectation that you're going to be using it often, because if you're going to be using it often, then the cost is actually pretty high in terms of performance. But if it's something that you're never going to be using, then the cost, or rarely going to use, then the cost for magnetic tape storage is actually great. And since you're never actually going to be sitting there and, fast forwarding or rewinding through the tape, it works out performance wise as well. So yeah, you absolutely can still purchase and use magnetic tape storage, and it's still used pretty much everywhere today. There are some downsides. So one of the upsides is it's cheap. It's really cheap. And it's small. They're really small. Like the magnetic tapes I've seen over in the post-production studios, they're really tiny now. I mean, the ones from like the 70s are huge, like these great big magnetic wheels like this. The machines are so cool to play with. But the new storage that you see are tiny. Like they're just these little cartridges. I mean, obviously they're not as small as SSDs, but or thin. They're also a little bit volatile, but you get the point. It's small and it's cheap. But they are volatile in the sense that magnetic tape has a lifespan, and the lifespan is not that great. So I don't know if any of you have ever used a VCR in your life and a VHS tape, but the more you play a VHS tape, the more degraded it gets. Each time you play it, it degrades a little bit more. And some of this is, radiation from the sun can actually cause the bits to flip, which is really bizarre, but it's true. It does happen. They call this bit rot. And the longer the bit rot happens to magnetic storage, and VHS is actually pretty susceptible to it. So a consumer grade VHS has a really low lifespan. Industry grade, commercial grade magnetic tape has a lifespan of about 10 to 15 years. And one of the interesting things that happens to it is it can actually stick to itself. And then you have to actually like put it in this like makeshift oven and like bake it or heat it up so that you can actually get the tape to separate so that you can make a new copy of it. But of course, each new copy, because of a certain amount of bit rot, is going to be a little less than the copy before. So you usually want to make a new copy before it reaches the end of its lifespan. So, okay, interesting stuff. So yeah, magnetic tapes still used today. Then we have another form of magnetic storage, which we also, it's been around for a while and we've kind of stopped using it, but not completely. And that is the concept of a floppy disk, which has been around since the 70s. And they kind of died in the early 2000s. Like I have not had a computer with a floppy drive probably since 2003. Because I was like, who needs a floppy drive? Nobody. If you ever wonder, hey, where'd that save icon come from? It's some kind of weird boxy thing. That's a floppy disk. So what a floppy disk is on the inside, there is a plastic, it's a thin floppy plastic circle that's covered in the ferromagnetic medium. They're called floppy because the actual piece of to store your data. They're called floppy because the actual piece of plastic is floppy. The 3.5-inch discs were not actually physically floppy on the outside because they were encased in like a hard shell. I guess I can find a picture for you real quick here. For those of you who've never seen a 3.5-inch floppy disk. Let's find a nice picture here. Images here. We've got all our floppy disks in it. There we go. It's got all our floppy disks in it. There we go. So the little blue one is the 3.5-inch, which you would have seen in the mid 90s to about the early 2000s. That's a 3.5-inch. It's actually a hard casing, and they store 1.44 megabytes. And then in the middle, in the red, that is an actual floppy. Like if you hold on to it, and you can go like this, and it like flops around. That is a 5.25-inch floppy disk, which would have been used from the 80s and to the mid 90s. It stores about 365 kilobytes of data. And again, it's this, you can actually see in the 5.25 and the 8-inch in the black, you can actually see the platter inside. That is through that little window there. That is actually the disk itself. And then in the back, this one would have been used in the 70s. This is an 8-inch floppy disk. And I don't actually know what their capacity was because I never had one. But they're cool. So this is, again, it's the same idea as a magnetic tape, except instead of being, like an actual tape that has to be read and written in a linear fashion, you now have this round disk that you can do random I/O on. So the idea is that there's a read-write head in the disk drive, and this is going to spin, this platter is going to spin in this little box here, and it will spin to the right position and the read-write head will move so it can read from the correct position on this big circle. Obviously, these floppy disks here that aren't in the hard shell case, they were really susceptible to damage. Whereas the 3.5-inch in this nice hard case was a lot more durable than the other two. Definitely that was the case. These floppy disks were notorious for going bad. These ones did too, but not as easily. All right, that's fine. A bit of history for you. Now, what's interesting is that even though that's technology that we used for storing files on and taking them with us, mechanical hard drives that you use today are pretty much the same idea, slightly different constructions. So again, I'm going to show you some pictures off Wikipedia here. I wish I could actually show you like a physical drive in my hand, but I don't have any. So the first one is the concept of a hard disk has been around since about the 1950s. And this is a really tiny picture. I apologize. But what you're seeing here is this big tower of platters. Now, these platters, unlike the platters for the floppy disks, are not made out of plastic. These are actually made out of glass and porcelain, and the glass and porcelain has been covered in the ferromagnetic material. But the concept is the same. The platter spins, and there's a read-write head that gets positioned over the data where it can then read or write it. So you can do random I/O on this as opposed to a magnetic tape where the only option is to do linear. So that's a cool picture there. Let me bring up another one. Now I said that they're made out of ferromagnetic glass. If we actually look inside a modern hard disk, this is actually what you would see today. Please, though, whatever you do, do not open your disk drive up to see what's inside. This is an incredibly fragile system, and the likelihood of you doing damage to it is really high. So what you're seeing here is in this silvery color. It looks like it's metal, but it's actually not. This is the glass or porcelain that's covered in the material. And you can actually see there's a stack of these. If I had to guess, it looks like there's 3 platters in this disc because it's pretty thin. And then this silvery arm here that's docked in this little orange station. This is a read-write header. It's a stack of read-write heads. They don't actually move independent. But the idea is that this platter spins at a really high rate, and then that read-write arm right there is going to come in and actually be able to read different positions on the disk. But they all move together. They don't move separately. And to show you just how fragile they are, there's a lovely picture in here. There was another pretty picture I saw. Every person's nightmare. So what's happened here is somebody probably dropped it on the floor. And since the platter is made out of glass and porcelain, it's very, very fragile. So as a result, the platter has actually shattered. And looking at this here, you probably can't recover much data. You might be able to get some off this bigger portion of the disk, but these little shards, obviously there's nothing that you can do about that. There you go. Don't drop these. They're very, very fragile. Super, super fragile. And they have other disadvantages as well. And we're going to talk about some of those disadvantages in just a minute. So that is a mechanical hard drive. Again, it's still a form of magnetic storage. We still use these today. Like I have a couple NASs here. NAS, for those of you who are not familiar, network attached storage device. And they use mechanical drives like this because an SSD of the same capacity would be way too expensive. But you can usually buy these mechanical drives for reasonably priced. Let's just look up here. Computer components, hard drives. Yes, I'm using a second computer. I have 3 sitting on my desk right now. So it looks like the biggest one you can buy from Canada Computers right now is a 16 terabyte, and it's $420. And I have some 14 terabyte drives. I think I've got 4 of them, and they're still about $400, $400 or $500 a piece. So again, it's expensive for storage. These are expensive, but they're not so bad. If you tried to buy an SSD of equivalent capacity, it would be significantly more money. Like if we look at how much a similar SSD is, let's go over to the Canada Computers website and let's see how big of an SSD we can buy. It looks like the biggest one they sell is 4 terabytes. And the 4 terabyte drives are looking to be about between $650 and $1,250. So you're looking at the price difference as being like they're 4 times the price of the equivalent disk. So people still use these mechanical drives, but they are not without faults. They are very, very fragile, and as we're going to see in a minute, they're also quite slow. Now, what other kinds of storage do we have? Well, we have all different kinds of storage. We also have CDs, DVDs, and Blu-rays. And although these have all kind of disappeared, it's a form of optical storage as opposed to magnetic storage. And they're kind of an expansion on the concept of a record. So I don't know if you're familiar with records, but a record is a piece of vinyl, so like a plastic, where the rings have been etched into it, and a little needle plays it, and that makes the sound. And CDs, DVDs, and Blu-rays are kind of the same idea, except instead of having, an etching that a needle reads, it's an etching that a laser reads. And so they're called optical discs because it's about how the optics behaves will tell the computer whether it's a 1 or a 0. Now, CDs have been around since about the 80s, DVDs the 90s, and Blu-rays the 2000s, but again, they're kind of gone. Nobody really uses them anymore. The other thing about them is while it was you could write to them, it was really expensive to write, and the compatibility for writing and then being able to read that disc back was kind of funky with the DVDs and the Blu-rays. And the other downside of them is that there was a very limited number of times that you could write to these, whereas if you're looking at a hard disk, the number of times that you can write to them is orders of magnitudes more than these optical discs. The other thing is that optical discs were really susceptible to any kind of physical damage. So they were nice. You could hold them in your hand and they weren't going to break unless you really put a lot of force on them. But they could get scratched, and the scratching would cause skipping or them just not to work. And then, of course, we have solid-state memory. Now, what's interesting about that is that's actually been around since the 70s, but it hasn't really been feasible until the 90s. And even then, I want to say in the early 2000s, when SSD started to become a thing, the quality was not so good. I remember I bought an OCZ solid-state drive in about 2008. And they had a failure rate of 35%. That's really bad because you can't really recover data off of them. They're really great now. Like all of these computers that I have in front of me are all using SSDs now. And I don't have any problems with that. And then something that's kind of new that's come up in the last little while is this thing called RAM or resistive RAM. And the idea behind that is just that it's RAM that has power, so it keeps its data after you shut the computer off. All right. Let's get into disks a little bit more here. I'm sitting here rambling over the history of storage, but you can't blame me. I like devices. Going computer and computer part shopping is super exciting. I'm not gonna lie. All right, so a hard disk, if we were to look at it from a diagram, it's a spindle, which is going to spin, and a bunch of these platters. And then for each platter, and I know I haven't drawn it here, there's going to be an arm with a read-write head. And all of the read-write heads actually move together. They don't move independently. It's not that you couldn't design a device that doesn't move them independently. It's just that from a mechanical perspective, that was either not cost-effective or there were issues with the actual implementation. So what actually happens and why these devices are actually so slow is because in order to find your data, two separate motors actually have to engage to physically find your data on the disk. So what happens is the platter is always spinning, and then you don't want it to stop. These environmentally friendly drives do stop the platters, but you'll hear them spinning up and spinning down. And that's going to actually increase the amount of time it takes to get your data, because if the disk is spun down and then you decide you need to get something off of it, the disk has to spin up, and the spin up process actually takes time. Because these platters are actually spinning at something like 10,000 or more revolutions per minute. So they go really, really fast, but it takes some time to get up to that speed. So the platters spin, and then you have the read-write head, which is also going to need to move from the inside to the outside of the disk to find your piece of data. And what we have is the disk is organized, and this is a pretty bad diagram here, but it's divided into tracks, which are these concentric rings, and the read-write head has to be positioned over the correct track. And it cannot start a read or write until the correct sector, which is like a pie slice, is underneath the read-write head. So just another, Let's bring over this. Let's actually draw a little picture here. It'll be a bad picture, I'm sure, but whatever. So you have your, oh, that's a really bad circle. That's a horrible circle. Anyways, so you've got those concentric rings for the tracks, and then the sectors, it's like we've cut, imagine this was actually a good diagram, and there's the spindle in the middle. We've actually cut each of the tracks or cut the platter into like these pie slices. And then even though physically the shape of this sector is different from the shape of this sector B here, we are making the assumption that all tracks have the same capacity and all sectors across all tracks also have the same capacity. So sector capacity is most often 512 bytes. That would be a most common sector capacity. And then the idea is when you want to do a read or write, we have to move the read-write head so that it is over the correct track. And then we have to wait for the platter so that the correct sector will finally show up underneath the read-write head. And then once it does, we can start the read or write operation. So two motors have to engage in order to find your data and start the read-write process. And that can take time. So how much time? So the time to do an I/O operation, or the cost for an I/O operation, is broken down into three separate components. We have the seek time, which is actually the dominating cost here, is how long does it take to move the read-write heads to the appropriate track. So the maximum amount of time would be how long it takes to go from the innermost track to the outermost track, and the minimum amount of time is 0 because you're already over the correct track, which would happen if you were doing sequential reads and writes and data was stored on a disk in a sequential fashion, which is ideal for these disks, and we'll get to that. So the amount of seek time really depends on how far you have to move it. Typically, we don't actually know where the head is right now and where it needs to go to, so we usually estimate seek time as an average seek distance, which is the maximum seek over 2, and we'll talk about that on another slide. Then we have the rotational latency, which is how long do we have to wait until the correct sector has now positioned itself under the read-write head. This depends on the speed of the disk. So like a good disk, like when I was younger, disk speeds were often 5,400 or 7,200 revolutions per minute. But now you can get disk speeds that are well over 10,000 revolutions per minute. This is not a dominating cost. The platter is always spinning. So what happens, and what happens once the correct sector is underneath the read-write head, we don't stop. This keeps spinning, which is why even though you can move the read-write head at the same time the platter is spinning, since we never actually physically stop the platter when it's at the right spot, until we always have to wait. Once the head's in the right spot, there may still be some rotation that we have to go through for the platters itself. So the maximum wait time here is the cost to spin the disk around once completely. The minimum is 0. By chance, we just happen to be over the correct sector. And then the third cost we have is the transfer time. So once we have the head in the correct position, how long does it take to spin the platter through the sectors that we actually are reading? So how long, if we're only reading one sector, how long does it take to spin through one sector, which would be 1 divided by the number of sectors per track times the maximum maximum rotational latency. If we were reading 2, it would be what fraction of a rotation is 2 sectors. And so the request service time is the sum of these 3 costs. So it's seek plus rotational latency plus the transfer time. It's expensive. So there are some formulas here, and these formulas are also posted on Piazza in the disk drive brief guide. But sometimes we want to know things like how many bytes are in a track. So we'll give you the capacity of the disk, so the total capacity. And we'll say, how many bytes are in a track, how many bytes are in a sector. And then we'll ask, what's the maximum rotational latency? What's the average seek and average rotational latency? And there's formulas here. The average is going to be the maximum divided by 2. At one point, we used to actually go through why this is true. We're not going to do that. You could take this formula as is and just run with it. And then we have things like the sector latency, so how long does it take to transfer one sector, and then we can compute something like what is the expected cost to read 10 consecutive sectors. So looking at this, just a little example here. So those were the formulas on the previous slides, and then on this slide we actually go through all of the answers for this little example here. So the number of bytes in a track, you take the number of bytes for the disk, and you divide it by the number of tracks that there are, and we see that there is 2 to the power of 12 bytes per track, which is 4 kilobytes, by the way. And then to figure out how many bytes are in a sector, you take the number of bytes per track, which was 4 kilobytes, and you divide it by the number of sectors. And then you realize there's 2 to the power of 4 bytes per sector. It's a make-believe disk, okay? And then to compute the maximum rotational latency, we haven't really given you much to go on here, but the maximum rotational latency is 60, which is the number of seconds in a minute, divided by the number of revolutions per minute that you have. So in that case, we got about 6 milliseconds here. So to compute the average seek time, we see that the maximum seek time was given by the disk manufacturer. So the average seek time is 10 milliseconds. And we always use the average seek time when we don't know how far the read-write head has actually moved. And similarly, if we don't know exactly how much travel the platter has gone through, we would use the average rotational latency, which is the maximum latency divided by 2. So we get an average seek time of 10 milliseconds and an average rotational latency of 3 milliseconds. You can see here the seek cost is dominating. And this is still true today. Average seek times today, you're looking at, for a high-end commercial disk, you might get a 3 or 4 millisecond seek time. But for a consumer disk, you're looking at 7 to 12 milliseconds for seek time. So it's still quite expensive. Cost to transfer one sector, we know that it is, go back here. So the sector latency is the maximum latency divided by the number of sectors per track. So in this case, we have the maximum latency as being 6 milliseconds. So that's rotational latency. And we divide that by the number of sectors we have per track. So that tells us it takes us 0.0195 milliseconds to transfer a sector. So then if I want to transfer 10 of them, it's 10 times the cost of one sector. So then the expected cost to read 10 consecutive sectors from the disk is the average seek time plus the average rotational latency plus the transfer time for the 10 sectors. So you get about 10 or 13 and change milliseconds. It's not free. So that's just a very rough overview of the costs. And again, it probably makes more sense for you to go through the guide and go through some of the sample problems that are provided in it. But just from a high level, one of the things that we know about mechanical drives is that larger transfers are more efficient than smaller ones, so long as the data is stored sequentially. And the reason for that is if you look at the cost per byte, and the cost in terms of time to transfer each byte. If your large file is stored randomly as bits all over the disk, then it's going to be super expensive. But if your file is stored sequentially, like on the same track, the cost per byte is going to be minimum. So large sequential transfers are way more efficient than random ones. And the reason is this. You only have to move the read-write head once. So if you're doing a big sequential transfer, you will move the read-write head to the correct starting position, but then after that, you don't have to move it again. And when you see that the seek cost is the dominating cost, and if you had random I/O, you would have to move the read-write head for every single little block you have stored over the disk. You can see that for large sequential I/O, the cost per transfer is minimum. However, It's not actually how we store data on these disks. And the reason comes down to fragmentation, the same kind of external fragmentation we dealt with when we were dealing with dynamic relocation and segmentation. If we are making the requirement that every file is stored sequentially on the disk, then we're going to come across a situation where we can't actually store the next file, because even though there is space across the disk, it's not in one contiguous block. So we actually break up files kind of like paging, and we will talk about that more in the file system section. So what are we going to do? Since sequential I/O is not always possible, what we actually tried to do is to minimize the average request time. Is we want to minimize seeks on a whole, so we group requests together that are close together. The idea is we want to schedule the jobs on our disk so that we end up overall minimizing seek time. So how do we do this disk head scheduling idea? So what you have is jobs are arriving for your disk constantly because of on-demand paging, because you're saving some stuff on BitTorrent, because you're writing a file, because you're doing all of these different disk-related tasks. And the requests are, like, as I said, they're always showing up, and they're always very, very small, usually. And what we want to do is we actually have like this queue of all of the requests for the disk. And you can only do one I/O request at a time. It is a serial device. You cannot do two requests at the same time because the disk physically cannot be in two places at once. The platters do not move independently, and the read-write heads do not move independently. You can only do one request at a time. So how can we schedule the jobs to minimize, since they're queuing up, how do we schedule the jobs to minimize the seek time overall, while not starving any requests? Because that's something really important too, is you don't want to starve any of these requests out. Now, a very fair and simple method is first come, first served, obviously. And if we did that, and we're going to use the same sequence of jobs, these numbers refer to which track they're on, because that's the only thing we care about here. Seek is related to the tracks. So what you see is the read-write head starts on about track 53, 54, and first come, first serve. So we're going to go over to 104, then to 183, down to 37, back to 122, back to 14, back to 135. The point I'm trying to make is we're going to be bouncing back and forth. First come, first serve is very fair. It's very simple. There's no starvation, but you are not minimizing the distance the seek head travels in any way, shape, or form. So what can we do? So scrolling in the right direction helps. Another one we can do is shortest seek time first. And this is a greedy algorithm, but unfortunately it also starves jobs. But if you look at how efficient it is in terms of the disk head, it's great. We always choose the job from the queue that is closest to our current position. So when we are at 53, if our current queue contained these jobs, then the next job I'm going to do is going to be job number 65. And then from 65, I'll do 70. And then I will do 37, and then I'll do 14, and then I'll come back. So we are moving the disk head significantly less. But if jobs are always arriving here close to where my head is, then any job that's far away from the head is going to get starved out. So while this is definitely a more optimal approach, starving requests is not good, because that's you opening a movie in VLC and nothing happening. And that's where you get really, really angry. So what we do instead is this elevator algorithm, or it's also known as SCAN, and there's lots of variations of it. You've seen it before, probably if you've ever seen your BIOS or looked at your drivers. Variants of SCAN are used today. And what they do is, it's kind of neat. So the head is in a current position, and we are going to choose a direction to go. So let's say we go this way. So I am then going to go this way, and I'm going to service every request I see in order going this way. So in this example, we started at 53 and we chose to go to the high end, so the edge of the disk, the outer edge. And so I'm going to surface all of the requests in order. So I go 65, 70, 104, 122, 130, and then 183. When I get to the end and there's no more requests in front of me, I turn around and I go back. And that's when I'll catch requests 37 and 14. And when I get to the end there and there's no more in front of me, I turn around and I go back. There's no starvation here, because once you reach the end of the disk, the edge of the disk, you turn around and you go the other way. So they may have to wait. If you just turned around and a job appears at the edge of the disk, it's going to have to wait for you to go all the way down and then all the way back. But that's the maximum amount of time it's going to have to wait. You will get served. Guaranteed. You're not going to starve. So that is what modern disks do, or some variation of this elevator algorithm, to actually minimize the average seek time. And the thing to keep in mind is jobs are always showing up. They're constantly showing up. So then we have to look at the actual driver for this. And I think we've got just enough time to do that for now. So looking at the device registers for a disk controller, and again, this is just OS 161's disk controller, so it's kind of limited. We have a status register that keeps track of the number of sectors. We have a status register that's actually a status and command register that will tell you what is happening on the disk. But it will also tell the disk to do a write. It's also used to tell the disk to do a write. Sorry, I just want to make sure I've got the right command here. There's so many different commands. There's so many different commands. And then we have the command register for sector number. And between these two registers, these are how you're actually going to write to the disk or read from the disk. So if you read to the status register and then a sector number, and if you did a write and then wrote a sector number, that would cause you to write from that sector. Did a write and then wrote a sector number, that would cause you to write from that sector. A status register that keeps track of the speed. This can be used for estimating transfer times. And then we have a transfer buffer, which is where we are either going to put the data to write to the disk or we'll get the data that is read from the disk. And you'll see the buffer is 512 bytes, which is the typical sector size on a disk. Then the one thing we know about the disk is that we can only do one read or write at a time. We cannot have multiple operations happening simultaneously. And so what we are going to do is we are going to have a disk semaphore that's going to give us mutual exclusion on the disk. The other thing we're going to have is a completion semaphore. And this one is going to be a barrier here, and it's going to have an initial value of 0. And the idea behind this is the thread that wants to read or write from the disk needs to wait for that operation to complete before it can continue. So we have the second semaphore here to act as a barrier to force that thread to wait until the operation has completed. So what we do is we P the disk semaphore to make sure we have mutual exclusion on the disk. And so this is for writing. We're going to copy the data into the transfer buffer. We write the target sector number to the sector register, and then we are going to put the write command in the status register, and that is going to cause it to write. We P this completion semaphore to force us to wait for this operation to complete. When the disk has completed it, it will fire an interrupt, and then the handler will run. We will acknowledge completion back to the device by clearing out that status register, and then we will wake up the thread who is waiting for the write to complete, and then they can release their hold on the disk. Now, why do you have to put that thread to sleep? Because it shouldn't, if you are writing, you don't want that. Usually in your code, you need that write to complete before you continue with the next line of code. That's not always true with writes, but it's necessarily true of reads, because after you read, you probably want to do something with the data. So you need to make sure the data is there before you move on. And this is a way that we can put that thread to sleep so the CPU will actually be able to go about its own business, and then we can wake it up later. Now, the read device driver looks almost the same with a tiny change. So again, we're going to P the disk semaphore to make sure we have mutual exclusion. We write the target sector number. We put the read command in. Now, this time we don't have to write to the transfer buffer because we're trying to get data off the disk. We need to then go to sleep to wait for the data to show up. So we go to sleep, and then when the device is done, some 10, 20, 30 milliseconds later or more, it'll throw an interrupt. Another thread will get it and will acknowledge completion, and then we will wake up the calling thread, the original thread. The original thread can then take the data from the device register, that's the transfer buffer, and plop it into its own address space. It's not that this other thread couldn't do that. It's just that it makes more sense for the calling thread to do that. And then we can release our hold on the disk. Now, not every device driver needs to have this second semaphore. You only need the second semaphore if you need to force the caller to wait for the device to complete. So you can either get error codes off or transfer data off or something like that. So it's not necessary for all drivers. You'll notice in the clock we didn't use it. In the serial console we didn't use it. You do need it for a disk though. So that's pretty cool, right? All right. Trying to figure out what I want to do here. So let's briefly talk about SSDs then. So we've spent a lot of time talking about persistent storage and magnetic tape storage and how it works. And it's slow, but it's reliable. It does have a longer lifespan than an SSD. And it's lower cost. But in terms of performance, it's really poor because of the seek time and having physical motors. It requires more energy, more power. So laptops with mechanical drives, their batteries don't last as long. They generate more heat because there's actual physical moving components. And so people wanted to move to solid state drives, which have no moving components whatsoever. I wish I had one to show you, but it's buried in my computer. It would be too hard to pull out. SSDs, it's just a board with some chips on it. It's very boring. There's no mechanical moving parts. There's no magnetic surfaces. It's just a bunch of chips. And that means that it's going to use less power and it's going to generate less heat, generally speaking. And it also has the opportunity to be faster. But how is it actually implemented? So there's actually lots of different implementations of SSDs out there. Two of the big ones was DRAM. And DRAM required constant power to keep its values. And so what it had is it had a bunch of capacitors, which are like mini batteries. And the idea is that in with the transistors and all the chips. And the idea is that the capacitors store a tiny amount of charge that would be able to keep power to the memory cells. And then the capacitors had to be periodically updated from a master power source so that they were able to actually keep power to the memory. And so DRAM actually has an onboard battery so that when your computer is off, the battery has just enough power to keep the capacitors charged up. There's some obvious downsides to this method. Number one, you have an onboard battery and they die. And so when the battery dies, you're out of luck. But it worked for a time. What we actually use now is called flash memory or NAND gate flash memory because it uses NAND gates. And I'm going to admit I don't know what this means, but Wikipedia and the paper says it traps electrons in a quantum cage. And my understanding is this can actually survive for about 10 years before it will start to lose its ability to keep its charge. So it's just a different way of trapping electrons to keep power to the memory. But after about 10 years, my understanding is it'll start to lose its charge. And some disks, it might be less time than that. And so you might start to lose data after that. Just periodically plug it in and recharge it, right? Now, there's no physical magnetic media. So we don't have the concept of tracks. We don't have a concept of sectors anymore. That doesn't exist. And so SSDs have actually kind of been divided up like virtual memory. So we've actually divided it logically into pages and blocks. Now, it's a bit more than logically, but we do have it divided up into pages and blocks. And we perform reads and writes at a page level. The most common page size, by the way, for an SSD is obviously 4 kilobytes, because that's usually what we use for our page size in virtual memory. And you kind of want all of these things to line up so that transfers from disk for on-demand paging to memory are going to be as fast as possible. So you can do reads and writes at a page level. Reads you can always do at a page level. There's no exception to that rule. But writes are complicated. So if the page is clean, that is, it's never been written to, and clean on an SSD is not what you think. We always think of clean or unwritten as all zeros, and actually it's the opposite on an SSD. It's all ones. So an uninitialized or an empty page will be all ones. And if you have a new page you're writing to, you can do that at a page level. So if you're going from 1 to 0, that's fine. If you have to go the other way, let's say you wanted to overwrite a page, so go from 0 to 1 to overwrite or delete a page, you can't do that at a page level because it actually requires more voltage to perform that switch. And you can't apply a high voltage at a page level. You can only apply the necessary voltage to a block. And so if you are overwriting or deleting data on an SSD, you actually have to overwrite or delete the entire block, not just the page you wanted. So this starts to get interesting. And so we have some solutions for how do you overwrite or delete memory on an SSD. The naive solution, which is slow, is fairly straightforward. What you do is you have to read the whole block into memory. So you read it from the disk into memory. And then what you're going to do is after you've read you could be reading megabytes of memory. And then what you're going to do is after you've read all of the data from that block into memory, you're going to tell the SSD to actually perform the write to the whole block. So set that whole block back to ones, reinitialize the block. And then you're going to update the block in RAM so that it has the correct thing that you wanted to write in the first place. And then you write the whole block back to the SSD. That's the naive solution. It totally works. It's obviously a little bit on the slow side. So SSD controllers, they have a little controller on board. They do a little trick. It's a lot faster. It has ups and downs. So the idea is that they keep track between the file system and the pages on the disk, which pages are free, that is, they're clean, and which pages are not clean. And the idea is when you want to overwrite or delete a page, well, let's say you just want to overwrite, we will mark the page that you currently use as invalid and needing cleanup. And then instead of overwriting it, we're going to find a clean page on the disk, and we're going to write to that, and now your file uses that page instead. So we're going to just kind of shift where your file is being stored on the disk so that we are avoiding the issue of overwriting. Now, of course, we're going to have a translation table so that we can keep track of which pages are clean, which pages are not clean, and which pages the file actually is using right now. And at some point, obviously, there's going to be no or very few unused pages left over. And at that point, you have to do some garbage collection where you actually have to do the naive solution and clean up the disk. But the idea is instead of having to clean up the disk every single time, you're minimizing the number of times you have to do that. And I believe the driver, the software that's done to do this is called, the cleanup is called Trim, I think. Don't quote me on that. Trim hasn't worked very well. It didn't work very well in the 90s. It only really became supported in the 2000s, at least at an OS level, Windows level. Now, here's some interesting things about SSDs. They have a limited number of writes you can perform to them. So each block can only be written so many times before you won't be able to apply enough voltage to actually make the flip from 0 to 1. And you might be thinking, oh, it's millions or billions of writes. No, it's actually only about 100,000. There is a very limited lifespan to these disks. And since reads and writes, since we don't have to move anything, and the performance of sequential and the performance of random I/O on an SSD is essentially the same. It's not identical. It's pretty much the same. There's no real advantage for having data stored sequentially. So what an SSD does so that the whole disk wears down at the same time is they do this thing called wear leveling. They make sure that the data is spread and writes are spread evenly across the disk so the whole disk wears down roughly at the same time. Because what you don't want to happen, and some of the cheaper disk controllers, once a small percentage of the pages have become read-only, because that's what it will do. When you can no longer write to a block, it will mark the block as read-only or the page read-only. And once a certain percentage of the blocks and pages have become read-only, the controller will actually mark the whole disk as read-only. You don't want that to happen too early. So we wear level so that the whole instead of the disk becoming read-only because of like 1 or 2 pages, we want the whole disk to become read-only at roughly the same time. We do this wear leveling, which is actually one of the reasons why you should never defrag your disk. If you defrag a disk, and defragmentation is where you take a file which is scattered all across the disk and you try to put it so it's sequential on the disk. So it's a lot of reads and writes that are happening. If you do this on an SSD, number one, there's no real performance reason to do it. Whereas on a mechanical drive, there absolutely is. And in fact, when I was in the 90s, I defragged my disk every other day because it was so bad if you didn't. But on an SSD, there's no performance advantage for it. But number two, you're doing all these extra reads and writes, and you can actually destroy the SSD. Don't defrag an SSD. Very bad. So SSDs, very good in terms of performance, orders of magnitude better than a mechanical drive, simply because there's no moving parts, but they are not without faults. So for example, they have a limited number of writes you can perform, but they are less susceptible to heat damage and they use less power. So, pluses and minuses. I'm satisfied enough with them today that I use them in all of my computers, but they all also auto back up to a traditional mechanical drive storage unit. The last type of memory to talk about here really, really quickly is persistent RAM or ReRAM, which you may have heard of as being called 3D X-Point or Intel Optane. And this is RAM that keeps its data even when power is gone. The idea is it's high performance, so it's very fast. It's roughly it's about like an SSD, maybe a little bit better. But it's not meant to be used as a persistent storage in the way that you and I think of, oh, I'm going to download some files to that. What this persistent RAM is actually used for, and this will make more sense when we talk about file systems, is persistent RAM is used to store or cache parts of the files for a computer or a server where the data is stored primarily on a mechanical drive. So mechanical drives, as you've seen, they're very, very slow due to actually having to move physical parts. And so what this persistent RAM is used for is to cache parts of the file data in a faster storage mechanism, like a faster storage means, so that if there's things we're using very often, instead of always going to the slow storage, we can just grab it from the fast storage. So that is what it's used for. It's not really something I think a consumer would use. This is something that commercial companies would use. Something Amazon would find this useful because at certain times of the year, certain search topics in certain areas are going to be very, very common. And instead of going to the mechanical drives all the time, if they use the persistent storage, they'll be able to get those database records much more quickly than if they had to go to the other. So that is the end of devices and I/O, and I know I kind of went through some of this really, really quickly. In Thursday's class, we're going to go over A3, the last big coding assignment, and then after that, so that will be episode 19, and then episode 20, we will start file systems. Yay!